Hi there, I'd like to run through assignment number 13 for the statics class at mine, CEEN241, section D. If that really applies to you or not, I don't know. This is kind of going off of one of the previous lectures about learning better, and that is to teach people, and I'm not good at teaching people, so I thought that I would try. And so here we are. Anyways, I'd like to run through this problem, get a good taste for it. We'll see how it goes. We are asked for problem 4.152 to determine the resultant force and the couple moment around, and I think it's asking around 0.0. So that's going to be this guy right there. We're given this diagram, and we have two resultant force triangles, I'm going to call them, right? So we have this guy on the left, which is a triangle that extends like this, and then this guy on the right. And we know that it goes 9 feet and from point O to W, and then W to the end, or, however you want to think about it. So the first thing that we're going to do to really lock down this resultant force is we are going to find the distributed force. And the way that I think about this really is I think of this like these aren't actual physical triangles. These are diagrams showing how much load is dispersed where. And from previous lectures, you know that a triangle like this, for instance, we have most of the load over on this right half, and so that's going to be down here and down there. And obviously it doesn't necessarily matter here. It'll apply more to the second problem. For this, the resultant force is we're actually going to just add both of these forces together. So starting with force 1, we have our total area. So when you have like a triangle like this and you're asked to find the resultant force, what you're trying to do is figure out kind of the area of that triangle, but the area in terms of the total force, right? And so it's a little weird conceptually. Oh, we're in the wrong pen. The way I do it is the same way you'd find the area of a triangle, right? 1/2 base times height. This gives us the area of a triangle, right, typically, but in this case we're asked to find kind of the area of this resultant force in a way. So we're just going to find what our H would be, and that is W, right? And we know W to be 35 pounds per foot, right? So if we know W, we can substitute this in for our height because it's technically the height portion of our area. So when we do that for the first triangle, we're getting 1/2 base, which is going to be 9 feet, right? That's given to us. And then our height, which is our resultant force, or W. Yeah, it's just W. It's 35 foot-pounds, or pounds per foot. Put that in there, 35. And we're given, if I were to do the calculations, 157.5 pounds. 157.5 pounds. Okay, great. Now, we know the other one, and actually I should mention that this is negative because it is in the negative y direction. Remember that. We're going to do the same thing for triangle 2. Nothing changes. You have 1/2 BH, base times height, where that is equal to 1/2, 9 feet, because that's your base right here. And our height is going to be 35 again. Now, 35 is going the positive direction, so this gives us 157.5 pounds. Or, yeah, I guess that's, in pounds. And you'll notice that these are equal and opposite, and they're just going to equal 0, because it is a perfect couple moment. That's kind of the first step, so if you were to plug this into web work, 0 is going to be your first answer. It's a perfect couple moment. The forces cancel out. All right, for B, right, we are asked to determine the couple moment, right? Well, actually, okay, this is the resultant force. I misspoke. Resultant force. For B, we're asked to find the couple moment. Okay, so as you can recall, the couple moment is defined by the force at a particular point on an axis, right? Yeah, so we're looking for the line of action, where that force points on here at the centroid of the triangle in both of these cases, multiplied by the total length to give us the total couple moment. And in this case, right, we know, this is what I was talking about earlier, we know this triangle right here, and I'm just going to redraw it. You have your 9 feet, and your, yeah, we'll just keep it 9 feet. We know that the centroid of this triangle is going to be closest to the side with the most mass, right? And so in this case, it's going to be this guy. That means it's 2/3 times 9. That is the distance at which the centroid is from the tip of your triangle. So, that being said, I'm going to erase this because I don't think they'd like me writing in pink. Find couple moment, our solution is going to be, we know the force. We know the resultant force for triangle 1, right? Triangle 1, and for triangle 2. Now, we just need to figure out where at which point does the couple moment lie on each of these triangles so that we can multiply the resultant force by that couple moment. So, for the first triangle, we see that the bigger side is more to the right, so it's going to be 2/3 times 9. 2/3, right? It's 2/3 of the way along this base, times 9, which is our total distance, right? 9, multiplied by 157.51. Remember, that's a negative, and so we are going to get 157.51. I wish I had my calculator handy, because this would be very nice. You know what? We're going to do that. Calculator. Alright, calculator. 2 divided by 3. Oh, shoot. There we go. 2 divided by 3. Right? Times, we multiply this by 9. Times 1, 2 divided by 3 times 9 times 157.51. Alright, we're given 945.06. 945.06 foot-pounds. Because this is a moment, right? Moment is in foot-pounds. Now, we do the same thing for this other triangle, and you notice it is 1/3 this time because the bigger side is on the left. 1/3 times 9. But we also have all of this distance to the left to account for. So we're going to have 9 plus 1/3 times 9. Same thing we just did before. 9. We're all going to put this in parentheses so that you make sure to multiply it. 9 plus 1/3 times 9. That is your total distance that you're going to multiply 157.51 by, right? So plugging that into a calculator, you get 9 plus 1 divided by 3 times 9 times 9, all multiplied by 157.51. that's going to give us 1,890, right? So this is 1,890.12 foot-pounds. And we're going to take 1,890 foot-pounds and subtract 945, because this should be negative 06. So we're taking that minus 945.06, and we're left with 945.06 foot-pounds, right? Wonderful. So in the answer, it asks us to give our answer in thousands of foot-pounds, or KIP.FT. KIP.FT. Now, that's a funny little way to say it. Anyway, that means that 0.945 KIP.F, 1,000 pounds per foot. And that is our answer. Anyways, just to recap, first thing we did is we found the resultant force. We treated each of these triangles like an area. And doing that, we also treated the height as W in this case, right? We found negative 157, positive 157. Added those together to give us the resultant force, which equals 0 because they're equal and opposite. And the next thing that we did is we found our couple moment by taking that resultant force from each of those areas of the triangle, finding the point at which it acts, or I don't remember what it's called. The centroid of each triangle, right? Finding the centroid of where the force acts, multiplying that by the total force of each triangle, and then we add that together. Remember, this is negative because this is negative, and so we have negative 945.06 plus 1,890, which gives us 945.06, translated to 1,000 foot-pounds per foot, or whatever you want to call it, is 0.945. Hope that helps.
Problem 0.54. Our given diagram here. We're given W1, which is equal to 2,000 newtons, and W2, which is equal to 4.5 thousand newtons. So we're going to kind of approach this in the same way that we did before for our last problem. And if you recall our last problem, we had this guy where we had two triangles acting on each other. The first question it's going to ask us here is figure out the magnitude of the resultant force. Now, from last time, we remember that the resultant force is going to be equal to the area that is under this, or the area of this shape. There we go. Area of this guy, right? And, that works because you can kind of think of it in the same way you think of an integral, right? The area under the load diagram represents the total force, right? Because integrating the load density over distance would add up all the tiny forces. And because all of these forces are constant, right? Then we don't even have to use an integral. We can just multiply it, right? And because of that, we're going to do the same thing. So we have and then we're also, I should mention this, we're going to kind of break this up into two different pieces because it would be a lot harder to find the area without doing this. So my approach is we're going to find the area of the rectangle below first, right? And that's going to be 6 times 2, right? 6 times 2 is equal to 12, right? And what I did there is I added up these two dimensions, right? And then we know that W2 is 4.5, W1 is going to be 2, and so if we have 2 here, we have 2 here, 2 here, we know this has to be 2.5, right? So we're just going to take this total area, right, which is going to be our 12, and we are going to add plus we are going to add 1/2, or the area of the triangle, 1/2, 6 times 2.5. And that is going to give us 7.5 total, right? So this is equal to 7.5 thousand newtons. This is 12. And so you're just going to add them together. So you have 12 plus 7.5 thousand newtons is equal to 19.5 thousand newtons, right? And so this is going to be your answer for part 1. I'm going to ask you for the magnitude of the resultant force. Because all we did was we treated it like the area and used W1 and W2 as those two heights. Alright, so the next part of this, find, it is asking us to, I apologize, I don't remember where this is. It's the distance. It asks us to find the distance we're looking for the distance of the centroid, right? So to find the distance of that centroid on the part, it's a little bit more complicated than doing the last one, right? Because we have this rectangle below, and then we also have this triangle, right? And you can't just magically add them together. And so here we're actually going to use a weighted average. And so this is given to you by the x centroid, right? We're going to have the force of the rectangle, right? So we're going to have rectangle multiplied by its centroid. And we know that if this is 6, right, this total length right here is 6, then half of that's going to be 3. So rectangle centroid is going to be 3. We're going to add that to the triangle, right? And we know that the centroid of the triangle, because our larger portion is on the right, it's going to be 2/3 whatever that length is, right? And so that's going to be, we have the triangle, the actual resultant force of the triangle, which is equal to 7.5. Oh, it's pink. 7.5, right? Or I'll just keep it in variables triangle. 7.5 times 2/3 times 6 times 6. And we can simplify this out and say that 2/3 times 6 is going to be 2, right? No, 3. Yeah. Oh, actually, no, I'm wrong. 6 times 2 is 12 over 3. That would be equal to 4. And all of this, because this is a weighted average, we're dividing it over the resultant force of the rectangle plus resultant force of the triangle. So this is going to give us x is equal to rectangle. We know rectangle to be 12 times 3, which is the rectangle's centroid, plus triangle 7.5 times 4. It's going to be centroid of the triangle plus 19 all over. I'll just write it out. 12 plus 7.5, which will be 19.5, just like we calculated over here, right? This, if you do the math, 7.5 is going to give you 66 over 19.5, which simplifies down to, or if you just divide it out, that's going to be 3.38 meters. So your total centroid of this whole shape, which is the rectangle and the triangle combined, that's going to be at 3.38, so somewhere around there, meters from point A. Alright, we'll run through the last one pretty quick here too. So right off the bat, we can see that we have a rectangle on our left and a triangle on our right. So the way we're going to do this is the same way that we kind of have been, right? We're going to find, number one, the equivalent resultant force. So that's going to be both triangle plus rectangle, the forces of those. So we know the triangle, or actually let's start with the rectangle, right? The rectangle is equal to 3 times W, right? And W is our resultant force here, and W is 700. So same thing that we did before. We're taking the area of that rectangle, which is going to be 3 times 700 equals 2,100 newtons. And we know the triangle, which is going to be 3. Well, actually, because it's a triangle, we're doing 1/2 base times height, so 1/2 base times 700. And so if you do the math here, this is going to equal 1050 newtons. And then something that I'd like you to consider here that's very important is all of this direction, or all of this force, is in the negative y direction. So we're actually going to have to make sure that all of these have a negative sign in front of them. If we don't do that, that'll mess us up later. So keep those negative signs in front of your solutions here. And so to find the resultant force, all we're going to do is add up. So resultant equal to minus 2120 plus minus 1050, right? And this is going to give us a total of minus 3150 newtons, right? So that's going to be your equivalent resultant force, triangle plus the rectangle. So for our second one, we are asked to find a couple moment at point A. Moment at A. Just to keep things neat. Our solution. So let's look at it. We're asked to find a couple moment around point A. And we know that all of this force here is pointing down, and if you remember, a clockwise direction indicates negative coupling. So keep that in mind. This will all play into that. When we're actually going about finding this, we're going to take, it's going to be the same thing that we kind of did before. We'll find the centroid of the rectangle, right? And we're going to find the centroid of the triangle and then multiply, and we'll keep these separate, right? So we'll have the rectangle, you find its centroid, whatever force is going down, and you multiply that centroid by the total resultant force in that rectangle, right? And then you're going to add that to your triangle, where you find the same thing. You find the centroid multiplied by the total resultant force in that triangle, right? And that's going to give you the total moment around A. So we can start off by doing that, and we know that our rectangle is minus 2.00 newtons, right? We know that we have to multiply this by our centroid, and our centroid is pretty easy because this is just a rectangle. The force is evenly distributed, so it's just going to be 1.5 meters, right? 1.5 meters. This is going to give us 3,150 Newton meters about A. And we're going to do the same thing for the triangle. And remember, when you have your bigger side towards the left, that's going to be 1/3 times 3, or the total distance here, right? Because that's where the concentration of mass is. So first we're going to do the same thing just to keep it neat. we know our total resultant force of that triangle is going to be negative 1,050 newtons, right? And our triangle, the centroid of that triangle, right, is going to be 1/3 times 3, which is going to be 1. But you have to remember that we're all the way out here and we're measuring off of A, so you're going to have to add up all of this plus that 1/3 times A. So that's going to give you 1, which is the centroid of the triangle, plus 3 meters, which is the other distance that's unaccounted for. So doing all of that, right, that's going to give you 4 times 1,050 newtons, which is going to give us a total of 4,200 newton meters about A. Now, quick reality check. Even though the negatives are down, right, you're going to want to make sure that you understand which direction this is going to move. And just using your common sense, if you have force acting this way on an arm, right, then the whole system is going to move this way. And this is in the negative direction if we define this to be positive, which is typically what we've done for all of our moment calculations, right? So we have two negatives that seems to check out, and we're just going to add them together. So negative 3,150 plus negative 4,200 newtons is going to give us a total moment about A of, negative 7,350 newton meters. That's going to be your answer for the moment about point A. Let me know if you need any clarification or what you'd like to see differently. This is mostly so I can learn this a little better, but if it helps someone else in the process, then that would be great.